it's rolling. We're continuing on with the harmonic oscillator. I believe that we finished the tricky method using the ladder operators. I was totally going to give you a quiz today about the ladder operator stuff. And you know what I didn't do? I didn't write any quiz questions. So I'll give you a quiz on Monday. All right? Okay. So now we're going to look. Question?
After the lecture today, I have a question on the homework.
Oh, okay. Actually, why don't we talk about it now, because that that we can get out of the way. What questions do you have?
It's actually just a fairly simple question, but I was wondering for the second part, when we have our OSI equals some function times psi, do we treat that psi as part of, or
Okay.
do we treat that psi as just like a placeholder?
So for instance, you have, I'm trying to remember, do you have it in front of you so you can just put,
Like O1 equals x cubed times psi.
okay, so we have that. So what we're going to do then is we say that if I have O1, oh, that's a Q, perfect. O1 comma O2 acting on psi is equal to right, we have to do it like this, and then we say, well, what is O2 psi? And what is O1 psi? So we have to know what both of them are. So if you have in front of you, what is O2 psi?
X dx, or x times d dx times psi.
You notice that these were only the ones that we found to be, all right, actually I said. And so if I put this in, it's going to be equal to and then I go on. So what I've done is in the brackets, I put operator 2 psi and operator 1 psi, respectively. And then I put in the second line, I put the operator 1, and then the brackets are the same thing. And operator 2, the brackets are the same thing. And so now we just put that all together. And so the first one is going to be x to the fourth d dx of psi. Right, that was very simple to put together. The one on the right is not quite so simple. It's going to be x times 3x squared psi plus x cubed d dx psi. So here I've expanded out the second one, and then we see as must happen if it's a linear operator, this and this subtract out, and I'm left with just a term that is equal to minus 3x cubed psi. And so that's,
When I was doing it on the homework, I was putting an extra sign there, so it made everything super confusing.
and so now that we're at this state, can you read then what is that equal to, the commutator? Yeah. Just making sure that you can take the the equation then and read what the commutator is from it. Okay, did you have another homework question? Nope. Okay then. So the work we did with the ladder operators was a very creative method of doing it. And it was a method that gave us some real straightforward outcomes. Now we're going to do it the analytical way, which means we're just going to do brute force math. Chris, you're a math major, right? So this should be your forte, except for mathematicians are looking for creative ways to solve problems, not looking for the brute force way of doing it. So we start by defining this crazy Greek letter xi. Xi. I would not use this myself, except for it's what our textbook uses. I have a problem writing it. I get myself all confused because I try to write too quickly instead of being artistic, and I forget how many loops there are. But that's what the textbook uses. So we have our Schrodinger equation. We've seen it 100 times. Well, maybe not 100, but a little hyperbole is never a problem between friends. We're going to replace x with a new variable. So we're going to define xi, the 3 equal sign, defined as square root of m omega over h bar times x. So it's just rescaling x, if you will. And then we're defining a new constant k. K is not kinetic energy or anything like that. It's just a constant k that is, actually, it's, I think, a constant kappa. I think about it, capital kappa or something. 2 energy over h bar omega. The reason we do this is to make the Schrodinger equation for a simple harmonic oscillator into a simpler form. So if you look at the first term in the Schrodinger equation, the kinetic energy operator acting on psi, if you use the conversion of variable from x to xi, because it's a second derivative, you're going to have the thing that's in the square root come out twice, so it's not square rooted anymore. And when you multiply through, it's just minus h bar omega over 2 times the second derivative of psi with respect to xi. So it's a much shorter way of writing this second derivative. Much shorter. It still has a constant out front. That's why we have the k is 2 over h bar omega. Because you see h bar omega here, the over 2 and h bar omega over 2, they are going to be things that we can get rid of. We just cancel things out in the end. So likewise, we look at the second term. When we do the change x to xi, we're going to have this term again squared now because we just substituted x is equal to square root of h bar over m omega xi. It's inverted of what we had before. It's 2 times, so it's squared again. And we have the same factor of h bar omega over 2 times xi squared psi. So with these substitutions, our Schrodinger equation becomes the second derivative of, well, let's actually do this rather than take it on faith. Right, the textbook, I think, just shows this. I'm not sure if it shows the intermediate, but let's show the intermediate. So taking what we found from above. So you see I've got the split screen, the half of the last slide and the top of this one. So my first term will be minus h bar omega over 2, not partial here, d second d xi squared. You can see how competent I am at x's. I tried to fix my tip. I dropped my pen directly on the tip and damaged it. And now it doesn't always write well, in case you're wondering about the skips. So there's replacement of the first term. The second term will be h bar omega over 2 xi squared psi equals, and then for E, if I solve this here, E is equal to my K H bar omega over 2. So there I've made the direct substitutions for C in the first two terms and E in the last one. And what you notice is H bar omega over 2 now exists in every term. So I divide those out. And that's my full Schrodinger equation. So what's the difference in that and what's written below? The difference in that is this was moved over here and this was moved over there. So it's shown as a simple differential equation, which I will write bigger over to the right just because I want to talk about it a little. So that's the Schrodinger equation. It's a much simpler looking Schrodinger equation. Now this is specific to the simple harmonic oscillator because it's based on the potential energy function of the simple harmonic oscillator. It's not like we can always use this. So now we're looking for a solution. And we're going to start by making our first math decision. Find solution for very large Xi. Now, if Xi is very large, then what is Xi squared minus K going to approximately equal? You know, let's say K is 1, Xi is 2 billion.
C squared.
Yeah. So we're going to find the solution in the very large Xi case. Since Xi is linearly proportional to X, this is also in the very large X case. That is for very large amplitudes. Then this is just approximately equal to Xi squared psi. Now you're both in differential equations. Have you gotten to the point of solving something like this? It's not linear.
I think we're just getting into nonlinear. Yeah.
Okay, so yeah, I didn't think you would, but I was just asking to see because, you know, if you've already solved these, then great. So the textbook doesn't assume that you know how to do this either. It says, the solution of this has the form of that, and it's shown right here. Now, if we look at this, we have to remember what psi is. Psi is not just any mathematical function, it's our wave function. And our wave function has certain rules. Tell me the rules that you remember for the wave function, things that it must obey. Okay, our different states must be orthogonal. That's not one of the ones I'm looking for because I'm looking for a single one, not for all of them. That is a correct thing, though. Okay, let's start with it must be normalizable, and we can't have both of them 0 or else we don't have a wave function. Must be normalizable is the answer I was looking for. There's other ones as well, like it must be continuous. It can't have a discontinuous jump, and its slope must be continuous. But the one I was looking for is the must be normalizable. Well, this term here, remember, this is the solution in large x's. So I'm only worried about large x's. If c is large, what is e to the c squared over 2 going to be? Like if c is approaching infinity, what's that approaching? It's approaching infinity. I can't normalize approaching infinity. So that's going to require that b is 0 for it to be normal. Let's write it down. Normalizable. So mathematically, b was just fine, but this being quantum mechanics and this being a wave function, the b had to be 0, or we don't have a normalizable wave function. So that gives us, that's why it has the arrow to just a e to the minus c squared over 2. Because that's the only normalizable part. If a was also 0, we wouldn't have a wave function, so that would be not allowed either. That's what Chris had said. Now, do you feel good about this being a solution? I said it was a solution. I know you're used to having faith in teachers, but you shouldn't. I am perfectly flawed. I gave a test yesterday and I put down the Boltzmann constant wrong. I am most chagrined. So we should check and see what the second derivative of this function is. So let's do the second derivative real quick. Oh, that wasn't c squared. That was... I'm glad I came back here. See, I make mistakes. That was a sign, not a... So the first derivative would be bring down the derivative of the exponent. It's either going to be, for the a term, it's going to be c times 2 over 2, so c. And then repeating. And then for the second one, it's got the minus sign. So there's the first derivative. Second derivative then is going to be got to use the product rule. My son's taking Calc 1 right now, so I've been practicing the product rule. Okay. There's what I get with my second derivative. Is that what you got?
Why is there a negative in the first term's exponent?
Okay. When I take the derivative of this here, I'm going to have to bring down a minus 2c over 2 because I'm taking the derivative of the exponent. And so, of course, the 2's canceled, but the minus sign stuck.
Well, I mean, like in the second derivative, the first term there, in the first term of the second derivative.
That's a mistake. See, once again, don't trust teachers. Or maybe I should just say don't trust me, but no, trust me as much as any other teacher. Okay, yeah, I misunderstood. You were pointing out a real flaw. So now, is that a solution to our Schrodinger equation there? And somehow I feel bad about my answer. Oh, yes. I'm okay with my answer because in our limit of very large C's, that one is meaningless, right? Because this is, if I factor, that's factoring out what we just did. And so the one is insignificant compared to the C in our range. So it wasn't perfect, but it was really, really close. And in our range that we did the solution for, it's fine. So yeah, I did this morning because it just didn't feel right to me. And yes, I had to remember the range we're in. So here is our solution for large C's. That's not our solution, it was only for large C. And so now we need to say, well, what's our full solution? Our full solution must be some other function multiplied by the solution for the large C. Now, since B was just a normalization constant, I can put that into this new function without any loss of information. So that's why we don't carry along an additional B. That B is just now part of the new function H. And according to Taylor's theorem, any, quotes, well-behaved function, which our wave function must be, can be made from an infinite sequence of polynomials, from an infinite polynomial. And so according to Taylor, no matter what this function really is, no matter what H really is, it can always be written as a polynomial, some constant times, well, H to the 0 plus some constant times H to the 1 plus some constant times H to the 2, etc. And so that's what we're going to do. We're just going to put in this Taylor series, this infinite polynomial, and then put it back in the Schrodinger equation and see what we get. Excited yet? Yeah. Yeah, this is just a kick in the pants is what this is. So now we're going to, for all C's. Before we did for large C, it was simplified. For all C, I have to have my full equation, the full Schrodinger equation. Second derivative of psi. Let's do that over to the side. If this is psi, then the first derivative of psi with respect to C doing the product rule. So there's my first derivative. I guess I should make you guys do the derivatives. You guys are the students after all. You don't need me doing calculus. That way, if there's mistakes, it's you that made the mistake. So since I've been picking on Indy, on Christmas time, Indy, what's the second derivative going to be?
Okay, so the second derivative is going to be, so you need to do more product.
Yeah, that's right. We can do product rule twice now.
Yeah. Okay, so the first term will be the second derivative of h. Right, so, yeah, and then I just did that, and then plus and minus.
I did it before as plus, but since it's the same thing as
So then times DHD C times C, then e to the negative c squared. And do it again. So there's 3 this time.
no. Oh yeah, you're right. There is. Yay! So what do we got?
Product rule for this one is just for whenever there's 3 terms, you just do one at a time.
That's correct.
So then it's DHDC times C times e to the negative c squared over 2. And then minus h times e to the negative c squared over 2. Then plus h c squared e to the negative c squared.
Okay, now let's collect terms and try to simplify this a little bit. Notice that these two are identical and that all of them have e to the minus c squared over 2. So this is equal to that's as simple as we can write it. 4 terms. Well, 3 with my factoring. You can see why I did it here and just have the answer here. So that's what we got from the second derivative. It has to be c squared minus k times h e to the minus c squared over 2. So moving this over to here, that's going to the e squared h e to the stuff is on both sides. Right, the term that has this is on both sides, so it's going to subtract out. And so the 1 stays the same, and then I'm going to have a k where the c was. So this must be true, or c must be infinity. Now we've already established as c approaches infinity, it's going to go to 0. So this here was our large C, doesn't need square, solution, it goes to 0. Now we need to solve then for all the rest of them, this equation that d second h d c squared minus 2c dh dc plus k minus 1 h is equal to 0. So that condition is going to have to be true for our entire range. So we've gone from the Schrodinger equation, a second derivative equation, to what looks like a more complicated equation. And then we're going to use our polynomial function h. So let's take some derivatives. So given our original h function, h is equal to sum over j equals 0 to infinity a sub j, c to the j, then taking the first derivative is actually pretty simple, right? You just bring down the j and lower the power to j minus 1. So it looks exactly the same. What's going on, and make the color more outstanding, what's going on from there to there? What happened? Because it's a little more complicated than it looks like at first glance.
I'm not sure why, but we changed our J's to J plus 1.
That's right. We changed our j to j plus 1. The reason for doing that is so we can have the summations for our original function, our first derivative, and our second derivative all have the same sum from j equals 0 to infinity. And so that's the reason for it. So it's important to understand that what we did is effectively, let's say, okay, I don't know how that shows up for you, but it's hard to read for me. I was trying to think of what's the best way to do this. That was J. So that's effectively what we did. And then we just changed from M back to J. One thing though, this is from J equals 0, and this was from, J equals 0, and then I'm going M plus 1 equals 0 is my starting point. So that would be actually from M equals minus 1, if I'm going to be consistent. But if M is equal to minus 1, then I would have minus 1 plus 1 right here. Minus 1 plus 1 is by definition 0. And so technically, I'm summing, but the first term is just a 0, and so it's not affecting anything. So I just added an extra 0. But I want to point it out so you don't halfway through say, wait a minute, you changed the index, but you didn't change the range of the summation. Okay, so now we're going to take the second derivative, and so we'll take this function here that we found for the first derivative, take the derivative of that, so we still have the j plus 1, the a sub j plus 1, but now we have to bring down this j, so that j came here, and the index goes to j minus 1. Let me, instead of using circles versus underlines, just change color. There. And then we go through the same trick of shifting the summation index. So I'm not going to go and show you the summation index change again because we've already done it once. So now we have the original function, first derivative and second derivative, all the polynomials, and we're going to put it in. So I'm going to put the second derivative here, first derivative there, my original function here. All of them had e to the j, so I bring the e to the j out. And since this technically is the Schrodinger equation, I still have the e to the minus c squared over 2 for the large c solution. So just to make sure that we've got everything straight, j plus 1, j plus 2, a sub j plus 2. I'm going to shrink this down so we can see both pages together. So there's that. And then we had 2 times c times the derivative. So that's, wait a minute. Yeah, 2 times c times derivative of h. Trying to straighten my brain out here. Is there supposed to be a c there? Yes, there is. Oh, yeah. So the derivative of h is going to be j plus 1, a sub j plus 1, right? Let's just do that one separately. There's my c term. And then I have the derivative term, which is I see where my mistake is. We're good. Well, it's not a mistake. What I did not think about. We still have the this function out here, the e to the c, e to the c, e to the c. I kind of forgot the, or not e to the c to the j. I don't know where my thought is. So for the second term here, for this term here, we're actually going to use this form so that we have 2c dh dc is equal to 2c sum over j equals 0 to infinity, j a sub j c to the j minus 1. So that's using the non-shifted form because we have this times this. Right, the j, either the c to the j minus 1 times c is c to the j. And so that's why that term just has the 2j a sub j. A sub j, 2j. Different order, but that's why that term is as it shows. And then the last one, the h, well, then we just put in the original h function here, a sub j, and then c to the j. Factored out the c to the j everywhere and the e stuff. interesting thing about this is we have j plus 2, a sub j plus 2, and then we have two places where we have a sub j. So we combine the a sub j terms and we have this thing here. Since the a sub j and a sub j plus 2 don't have to have any functional relationship, I'm going to have the coefficients of each one independently go to 0. So I'm going to have, yeah. You're going to have k minus 1 minus 2j equals 0, and let's see, trying to make sure I've got this right. No, that's yes, I didn't think this through carefully. Now what I have is I have a relationship between a sub j plus 2 and a sub j. There was no fixed relationship. This is giving me the fixed relationship. So I'm going to have that is going to have to be 0 for each level of c raised to the j. And so it gives me a relationship between the a sub j and the a sub j plus 2. I can just take this, move this across to the other side. Change the signs of everything. So 2j plus 1 minus k. And then divide by what I had on the other side. So that is an equation that has to be true if I'm going to have a solution. So now I have an equation that allows me to relate the A's for each level. Because my a sub j plus 2 depends on a sub j, then really a sub 0 and a sub 1 are the only independent variables, and after that, each a sub 3 or a sub 2, a sub 3, a sub 4 is something that I can build up from the starting to a sub 0 and a sub 1. Now, an important thing, I once again remind you that I have to have a normalizable function, which means that my polynomial has to terminate at some level of j. If we get to infinity with j, then we're going to have a function that doesn't approach 0 as c approaches infinity, and thus is not normalizable. So it has to terminate, it has to end. The a sub j's have to be 0 at some point. And so that termination at the highest level, we set n to be the highest level, or specifically the level where it terminates. So a sub n is 0, and every a sub n beyond that is 0. So, or every a sub j beyond n is 0. So n, as you might recognize, is an important quantum number for us, and it's going to tell us which term terminates. And because we had a sub 0 and a sub 1, two independent things, it's going to turn out that a sub 0 or a sub 1 has to be 0, depending if we're doing even numbers or odd numbers. It's, got 3 minutes, I'm like looking at the clock, can I get out of this? So we start at our end position. We say, okay, for terminating at n, a sub n plus 2 is equal to 0, and then I just put in for j n everywhere. And that gave me a relationship that K must be 2n plus 1. That is, just say it's setting 0 is equal to 2n plus 1 minus K means the numerator has to be 0 when you're at n. And so saying the numerator is 0, 2n plus 1 minus K equals 0. Very easy to solve for K. And K related to our energy. I believe it was K was equal to 2E over h bar omega. So therefore, the energy is equal to h bar omega over 2 times K. And so with that solution for K, well, that was a silly way of writing intermediate. All of these are equivalent, but we now have a quantized energy. Exactly the same energy that we found with the ladder operators, which makes me feel kind of good. We don't have a wave function yet. We don't have a wave function yet because we have to find all of the different a sub j's if we're going to have our wave function. But we now have the energy. So how do we get our wave function? Well, we're going to have a normalization constant, this thing and this thing. And then this here is the actual solution to this equation. It's called the Hermite polynomial. So there's a name for that solution, the Hermite polynomial. And people have, gone through and calculated what you're going to have for each a sub n with your starting conditions. Two different ways to do the solution for the simple harmonic oscillator. One was very tricky using the ladder operator. One was pretty straightforward, brute force. Neither, I would say, was easy per se, but they both get you done. They both get you there. Why do we do both of them? We do both of them because the methods here are methods we're going to use again. Find a solution for large h. The next problem we're going to do like this, we're going to find a solution for large h, let's go back to x because it's easier to say. We're going to find a solution for large x. Then we're going to find a solution for small x. Then we're going to say, now there must be some polynomial for the solution between the two. Right? So we're going to expand on that idea in a further problem. It's a hard math plus a hard conceptual idea when you get to quantum mechanics. Any questions?
So K is just a relationship between, just to make a relationship between energy, right?
K was a substitution to make the Schrodinger equation look simpler. Right, we go all the way back to the first slide here, where we defined K as 2E over h bar omega, so that our Schrodinger equation would come to be this very simple form.
Okay.
So the reason for K was to make a simple Schrodinger equation. Then when we found the value for K, we were able to take that definition and back out to find the energy states.